and I'm happy to introduce Gururaj Naik. Guru, first of all, is a close friend of mine. I know him for over a decade. Um, we've had some overlaps in the conferences in the US when I was a postdoc there and Guru was a PhD student. So basically, he graduated with a PhD degree from Shalev and Bolseva Group from Purdue. And he's really famous for discovering new plasmonic materials for nanophotonic applications. Then he moved on to do his postdoc with Jen Dione at Stanford. He spent a few years there. And in 2016, he started his own independent group at Rice University, where he's an assistant professor. The Guru works mainly on quantum nanophotonics and materials for applications in energy imaging and health. He's won many awards, such as IEEE Photonics Society Graduate Student Fellowship and a research award at Purdue itself. And Guru, he's a gold medalist from Indian Institute of Science. Indian Institute of Science is the #1 institute in India, and the first Indian director of Indian Institute of Science was Sir C.V. Raman, that I think most of us know. So let's welcome Guru. Guru is going to enlighten us with his talk on a phase transition for nanophotonics. The stage
Uh,
is yours, Guru.
yes, thank you very much, Ranjan. It's really nice to see you all, and thanks for this opportunity to share some of the research progress that we had and share my excitement with you all. And once again, I think this is a pleasant opportunity to meet people, which is and now really hard in this pandemic. And thank you all for making your time in this morning. And of course, also thank you Justin for helping in this webinar to come up and also hosting in the physics department. Thank you very much. Today, I would like to share some of the recent progress that we had with how to bring or how to make use of phase transition in nanophotonics. So before I actually get into the details like why this is important or what it is, etc., let's actually take a step backwards. Okay, and then I'll just talk to you about something that's more of an interesting or an aesthetically pleasing picture. Let's begin from there. Okay, so this picture, which is of course just a beautiful scene on a beach on a sunny evening, it just tells us two things. Of course, it's beautiful, right? So that's first thing that we notice. But for a scientist, this is more. It's just not that. It also talks about two things. So one is the global warming situation, which is causing problems, especially with rising sea levels. And that's a challenge that we have, a big societal challenge that our generation is currently facing. And also we have a solution for the same. So this for this problem, so which is sun, right? So we all know that solar energy, for example, can is one of the most popular renewable energy sources that can bring in a solution to this global climate challenge. Okay, so where are we with that? So what are we doing? So are we doing as scientists? What is our role there? So what have we been doing so far? So if you just look at, for example, the current efficiency of photovoltaic cells, so we see that the efficiencies in market, for example, the silicon solar cells are just about 22%, right? So why is it that low? Can we bring anything better? And the answer is yes, of course, you can change the material from silicon to gallium arsenide and your efficiency increases to 28%. And instead of gallium arsenide, you can also have multiple junction solar cells. So where each solar cell has a different band gap, you can boost the efficiency. In fact, NREL, National Renewable Energy Laboratory in the US, has shown that the maximum efficiency that you can get, even with 32 junction solar cell, is about 48%. So you cannot really go past 50%. While the corner efficiency is really high, right? So sun is a black body at 6,000 Kelvin, so that's your source temperature. and your sink is terrestrial temperature, so it clearly can go to very high efficiencies. So why don't we get that high efficiency? So where are we losing it? What's causing this problem? Okay, so this is where a lot of motivation for my research comes from. So what we do is, at least just to analyze the situation, just take a gallium arsenide solar cell, a single junction solar cell, where the efficiencies are close to 30%. Okay, so that's this green portion in this bar figure, bar diagram. Okay, and the rest of the efficiency that is lost, if you look at where it is lost, we see that 40% of efficiency is lost in photons not being used really well. So which is the photons from sun. So sun is just a broadband source. It's a thermal light source. Any thermal light source is really broad. It has all different colors, right? So we see red to blue, but that's only a small spectrum in the visible. You also have infrared photons. You also have many UV photons. So when we look at the energy of this photon with respect to the band gap of the cell, you can have a scenario where the energy of the photon is smaller than the band gap, and then you don't have any absorption in the solar cell. So that's some loss of efficiency. And the rest of the loss, in fact, comes because if you have energies like UV photons, which have energies that are significantly higher than the band gap, and that excess energy, that is energy above the band gap, that's just lost as heat. Okay, so this excess energy, just this electron, after it's excited, will just lose that excess energy by heat very quickly. So you're heating the solar cell partly, and then you're also not absorbing the infrared light. So both of them account for 40% loss in efficiency. So if we want to bring efficiencies of solar cells beyond this 30%, let's say for a single junction solar cell, then we cannot do that without controlling the properties or the spectral properties of the source, of the light source, which is sun. Okay, so we have to do something with controlling the spectrum. Somehow have to squeeze the spectrum of sunlight into a very narrow bandwidth. Only then we can get very high efficiency. So how do we do that? So this is where the challenge lies in. Okay, so let's think about a different way of doing it. Instead of thinking of photovoltaics, what if we think of thermophotovoltaics? So thermophotovoltaics is just going through an intermediate step of heat. So in this case, let's say we have the same sunlight, which is all different energies of photons. And then now I put a black body in front of it. Okay, so black body will not distinguish the photons based on their colors, based on their energy. For a black body, all these photons are just packets of energy, and it just accepts them, it absorbs them. So once it's absorbed, then all these photons just convert their energy, this optical energy, into heat in this black body, right? So the black body just becomes hot under sun. So now once I have this black body hot, then this hot body would also emit thermal radiation, right? So a typical thermal radiation from terrestrial black bodies, which are not like 6,000 Kelvin, but maybe 2,000 Kelvin or less. So the radiation will be still broadband, centered around infrared, not in the visible now. Okay, so we went from one broadband, which is sun, to another broadband source from the black body. So what's the point in doing that, right? So clearly that's of no use unless we do something, which is we put a filter here. So the filter has this kind of idealized property. So the property is, so if the photon emitted from this black body happens to be in the small bandwidth, okay, this is the pass band of the filter. So within this small spectral window, the photon would be released out, would be let go out, okay. But if the photon energy is anywhere outside of this pass band, the photon would be perfectly reflected and sent back to the black body. And the black body would just absorb it, right? So if the energy of the photon doesn't match this window, this pass band, then the energy of the photon would be recycled back into the form of heat and then stored as heat. So the only way heat can leave this black body emitter is through photons that fall in the pass band. Okay, so what we did in this process is we took broad bandwidth of sunlight, so many different photon energies, and then squeezed all of this energy into a small pass band of the filter. Okay, so once we have really narrow band frequency, narrow band thermal emission from the system, we know how to convert this to electricity very efficiently. For example, we can buy photodetectors which have quantum efficiencies close to 100%. In fact, 99.5 probably is the record so far. You can get nearly 100% quantum efficiencies. So, getting efficiency or efficient conversion of narrowband light to electricity is not a problem. We know that. Okay, so what thermophotovoltaics does is it takes broadband light and then converts into heat and then eventually heat back into light, narrowband light now, and then to electricity. Okay, so that's what this is called, solar thermophotovoltaics or solar TPV, STPV. So where the source is sun. But we are not limited to just sun. If we just think of this thermophotovoltaics, all it requires is just a source of heat. So, which is heating this black body. It can be light, it can also be some other form of heat. So, if we can get really high efficiency conversion with thermophotovoltaics, we could do it not just with sun, but also with waste heat recovery. Okay, which is, for example, in this case, automobile exhaust, or even in the case of body heat powered watches. Okay, and in fact, just to compare, NASA's rover, so which used a plutonium radioactive source to generate power, it actually used thermoelectric generators, not thermophotovoltaic generators, but thermoelectric generators. And if any one of you have checked, researched what is the efficiency, conversion efficiency of this one, it's less than 2%. Okay, so with less than 2%, then that was the state of the art. We were able to design systems that were able to survive in Mars. Okay, so instead, suppose we were able to get efficiencies like 15% even, that would be a game changer, right? So this is a huge market and an opportunity for nanophotonics community to address global energy challenge. Okay, and also just waste heat recovery, which is in fact with big industries like fertilizers, for example, chemical plants like oil plants, which are really famous in Houston, which is where I live. Houston is the energy or oil capital of the US. So, which is where all the oil refineries are located, where oil is refined and then goes to the rest of the country. So, in such places, we can even just see, just by driving across these refineries, how much waste heat is generated. And just from the data published by Department of Energy, this is just to give you a perspective. About 20% of all the industrial energy consumption in the U.S. is wasted, and Texas is a really big. It's, I think, the second biggest or maybe the biggest state of the U.S. Sorry for my poor geography, but just to give you a perspective, for this big state of Texas, this electricity, this energy is 3 years worth of electricity in the state of Texas. Okay, that's how much energy is wasted each year just because of this is actually the energy that is accounted for from the grid. And things like fertilizer industries, they have their own production plants, energy production plants, and they don't even go to the main grid, which is where all this calculations reports are prepared. So clearly there is a lot more energy that is wasted, and there's a huge opportunity for us to recover this energy and then make the system more efficient and thus reduce carbon footprint. Okay, so where are we with this thermophotovoltaics then? If it is so promising, what is happening? Okay, so here is what people have tested in the past. Why TPV is not used in Mars rover. So here is the reason why. Okay, so in the past, there are many different ways people have tried that. In fact, the highest reported efficiency so far is actually about 15%. In fact, close to 18%, but between 15 and 20. So that's about the highest efficiency so far possible. And anything better, it was really difficult to do. And what the nanophotonics community did is, let's actually think about how do we design this filter. This filter was really the bottleneck here in this filter design. So they said, let's actually make this filter functionality together with the black body emitter, which we call as selective emitters. So where the emitter itself emits in a narrow spectral window. So why don't we make such kind of devices which are easy, compact, and hence also present less challenges in terms of building a device. So that's what nanophotonics community started thinking about, which was somewhere close to 2000, the year 2000. Then since then, of course, many different devices based on nanophotonic filters came up. And again, all of them just have efficiencies that are much smaller than even this 18%. In fact, the state of the art so far is less than 10%, close to 8.5% efficiency. So why is this happening? So theory says we can get to 80% while we are not even a tenth of it. Why? So what is really causing this problem? And the problem is, as I mentioned, the selective emitters or this thermal light sources, they are basically held at very high temperatures. They're terrestrial black body objects held at very high temperatures, temperatures close to 2000 Kelvin. Okay, and at these temperatures, it's really difficult to find materials that can have low optical losses and then also can confine light really well. Every material degrades at high temperatures. Okay, its optical losses increase, and then also the nanostructuring that we need to make these devices, those just slowly melt away as we increase temperature. And that really limits the performance of these devices. So, which was kind of thought of as granted before, never got much attention, and only recently this has become a big impediment in going any further. And that's where my group said, okay, we can probably solve this. Let's look at it more carefully. Okay, so what we did was we first started with just building a model of the whole conversion system. So let's think of this selective emitter. So selective emitter is something that has an emission that is product of two things. So the first thing is just the black body radiation spectrum itself, shown in this pink curve. Okay, and on top of that, the selective emitter has a filtering functionality. So a product of these two curves is actually the emission spectrum from the selective emitter. Okay, so let's say that this emitter is somewhere between temperature 1000 and 2000, and then we have the black body emission curve corresponding to that, and the filtering functionality of the selective emitter is approximated by the step function. Okay, so we have in the bandwidth where we want to emit, let's say the emissivity is given by rho, which is 1 or 100% if it is really a good emitter. It can also go beyond 100% if you have focusing or concentration. And in the region where we don't want emission, let's say the suppression is some number. It's very small, but it's still some number. Okay, so we express this in dB. So we now build this model, assumed there's a PV cell, which is an ideal PN diode, and then modeled with some realistic parameters. And then what we found out was we also assumed that there is an inevitable phonon band of emission, etc., some non-idealities, which anyway happen in devices. And then with that, what we got was this is the gist of our analysis, that if we plot this normalized efficiency, so which is efficiency normalized to Carnot efficiency. So, and we chose a temperature of 1300 Kelvin, which is typical for most of the waste heat recovery systems. Okay, so what we found out was as we increase the emissivity, that is this rho in the desired spectrum, see, look at this, this is rho, and this is this S, which is suppression. Okay, so as we increase emissivity, our efficiencies go up. Okay, but they really don't go up so much. It's not that strong of an increase in efficiency, while suppression, so which is this vertical axis, has a dramatic difference. It makes a huge difference in terms of efficiency. So if we go from 5 dB to, let's say, 15 dB, my efficiency clearly goes from about 10% to 30%. That's a huge jump, right? So suppression is really a very powerful property or parameter that controls the overall efficiency of the system. And suppose we let to have some concentration, maybe put some focusing devices, collect it over a large angle, large area, and then focus the IR photons onto a very small area of PN junction, then that will actually give us some enhancement in terms of this emissivity. That is, this rho can be greater than 1. And in that particular case, we can have efficiencies even higher, actually much higher than 50%. Okay, so then why did people so far didn't do this good? So why were they stuck? And And if we actually analyzed all the previous reports and found that if we were to plot on this in this picture, they would all fit somewhere here where the suppression is about 5 dB. Okay. And emissivity, in fact, close to 1. So most of the past reports just thought about how to improve emissivity, but almost neglected suppression, because the suppression is extremely important and it has to be really broad wavelength range. So in a broad spectrum, we have to suppress emission of photons. That's really the key here. So how to do that? Okay, so this is a clean opportunity for nanophotonics where we can make a huge impact, and that's where, in fact, my group started thinking about how do we design a filter generally. Okay, if we want to design a selective emitter, let's think of two perfectly or nearly perfectly reflecting mirrors. So this is a 100% reflection. This is near 100%, but slightly less. And I put an emitter here, okay, a very thin layer of, let's say, some material which is just emitting thermal photons. So now these photons just go back and forth in this cavity, and at resonance, we have the peak in emissivity. That is, there is a huge number of photons coming out of this cavity. Okay, if I were to plot the emissivity of this cavity while putting different materials in this cavity as emitters, so if I put tungsten, which is a lossy metal, for example, okay, so we get a Q factor of about 45. So Q factor is my proxy for suppression. Okay, so if I get a Q factor of just about 45, that's the maximum I could get. But if I have semiconductors, lightly doped semiconductors, I could get Q factors greater than 1,000. Okay, so clearly semiconductors is one of the things that people should have been looking at, which in the past designs didn't happen. They're mostly metallic photonic crystals. So that's one of the reasons why they didn't achieve this high selectivity, okay, or suppression S factor. So that's one of the reasons. And the rest of the another problem, which in fact always haunts all of this device, is actually if you take any resonator, single resonator device, and for thermal emission, as you add more losses to this cavity, there are more thermal photons that come out of this material. Okay, so thermal emission requires absorption losses. So more absorption losses, more thermal emission. So you see brighter thermal sources with higher or lossy emitters. Okay, but higher losses will make this cavity to have smaller Q factors. So which means this Q factor of the cavity, that is selectivity, and the brightness of the emitter, they both trade off against each other. You cannot get best or two things simultaneously at their best. So there is a sweet spot for losses. So you cannot really have too high loss. You cannot have too small loss. So how to hit this right balance? So this was the problem that the previous designs had, and that's why they all, in fact, were not able to get high efficiencies. And then we took a step backwards and said, let's actually think of this from a more fundamental way. How do we even design a cavity? Okay, why do we even treat this cavity as just photons as just waves, and then there is resonance, overlap, the phase of the cavity as some 2 pi or integral factor of 2 pi, all these things based on wave picture. Why don't we look at this as a photon or the quantum picture of light? In fact, thermal emission was the one which inspired Planck to pick or to quantize the energy of light, and then eventually gave birth to quantum mechanics, right? So, though I think quantum mechanics was born from thermal emission problem, we almost totally forgot about the quantum property of thermal light and instead focused on only the classical part of the thermal light. Okay, so the quantum part was almost never utilized in nanophotonics. Okay, there were only here and there designs, but most of the designs were how do we confine light in a single cavity? That's what people did in the past. Okay, so in the classical nanophotonics, which I mean by classical photonics as photonic crystals, plasmonics, metamaterials, we focused on just making single resonators, and at resonance, I would change the density of photonic density of states, and thereby control thermal emission. That was the only way we controlled thermal emission. We almost forgot the other part of it. Okay, so what if we make use of the quantum nature of light here? How is it possible? Can we even do this? Okay, so for that, let's actually step back and then find out how do we write the mechanics of such a system, a thermal emission system. Okay, so thermal emission system is not a closed system. Why? In a closed system, energy is conserved. You don't have any exchange of energy with outside. And hence, we have observables as the outcome of the system. We have real eigenvalues, and this is Hermitian system. We know that the Hamiltonian is Hermitian, and Hermitian physics nicely captures closed systems. Okay, but thermal emitter is not a closed system, it's an open system. First of all, it has absorption loss. Without absorption loss, you don't have thermal emission. So that's one requirement. So clearly that makes it open. Plus you also have, it's a light source. So it's actually giving light out. So that makes it again an open system. So both of them make the system where we don't have energy that is conserved, not necessarily have real eigenvalues, and not always we have observables in the system. Okay, so how do we describe the system then? We cannot use Hermitian physics, but instead we need to go for non-Hermitian physics. Okay, so if we were to use a non-Hermitian physics to describe thermal emitters, that would actually lead us to the quantum optical description of thermal emission. And that would lead us to very interesting properties, which are like phase, symmetry, and topology, which we almost never care for in the single resonator or wave or classical description of thermal emission. Okay, in the classical description of thermal emission, geometry and materials. Those were the only two design parameters that we had, but now we have three more really powerful new design tools of design, so which is phase, topology, and symmetry. Right, so that's why we were really excited about non-Hermitian physics design, and then looked at how can we design this. A particular non-Hermitian system is the one which has parity and time symmetry. Okay, so let's actually look at this system. What is parity and time symmetry? So let's take two identical resonators. Okay, so one has optical loss, the other has optical gain here. Equal loss and gain. Okay, balance loss gain system. And let me couple these two resonators with a coupling factor kappa here. Okay, so I can write the Hamiltonian of the simple system by basically having this form where I have omega plus I times gamma as a lossy resonator with loss as gamma, and then the gain as minus gamma for the gain resonator, imaginary part. Okay, and then coupling is kappa, which is the off diagonal term here. So now if I apply parity operator, I would just do mirror operation here. So my loss and gain resonators would exchange their positions. And then now if I do time reversal, then I would just put gain to loss and loss to gain. That's what happens in optics. In optics, time reversal just means changing the sign of imaginary part or putting I to minus I. Okay, so that will just restore my system back to whatever I started with. So my system that way is parity and time symmetric. And why is this interesting? If we have parity and time symmetry, then the system exhibits interesting optical phase transition that is extremely useful for thermal emission. Okay, that's why we were interested in this. So first of all, there are two regimes here, two phases. Okay, so when this coupling constant kappa is really large, then what happens is these two resonators are so tightly connected, talking to each other, that they exchange energy faster than either the loss or gain in each of the resonators, and hence the total energy of the system would be almost equally distributed in the two resonators. Okay, that gives rise to two modes which have just real eigenvalues and no imaginary eigenvalue. Okay, so the imaginary part is zero, then just only the real part here, which just shows this Rabi split and then exchange of energy, which is Rabi oscillations, which we know really well. Okay, but what happens when we reduce this kappa? So as we reduce kappa, at some point, these two eigenvalues merge into one, which is called an exceptional point. And then beyond that, if we reduce the coupling factor, then the modes will be separated into two resonators. So the coupling constant is weaker than the rate at which they lose or gain energy, and hence the modes will be separated into these two resonators individually, where we'll have one that gains energy, one that continuously loses energy. So which means I have one that has imaginary part that is positive, another that has imaginary part negative, but the same real part. Okay, they both have the same real part of eigenvalue. And this is extremely important for thermal emission, because what I'm doing is I'm having the same resonant frequency, but I have two modes, one which has very high imaginary value, so which means it can actually take thermal photons from the vacuum fluctuations and then radiate out. And I have another one which has very small imaginary part, which can actually take this thermal photons and store it in it and then give very high selectivity, that is Q factors. Okay, so I can actually break this trade-off between thermal emissivity and spectral selectivity. So that's the reason why we wanted to pick the system. So what we did was actually a passive case of this PT symmetry. So where I use a very high loss resonator and nearly lossless resonator. Okay, so we made the high loss resonator by this tungsten plasmonic resonator and lossless resonator by silicon and coupled them both. Okay, so now the lossless silicon resonator has an electric dipolar mode in it, whose image, lossy image in tungsten is what they would be coupling with. And the spacer, which is magnesium fluoride, would separate the distance between these two, and hence the mode overlap, and hence the coupling. Okay, so what we did was, or what we think, or why we wanted to choose this is, we want ideally tungsten to give out all the thermal photons, and then silicon just to store these thermal photons in it and then leak out or radiate out with a very high Q factor. Okay, so that was the idea here. And we did even build a simple transmission line model, and S matrix analysis showed us the thermal emission, in fact, shows exactly that PT symmetric behavior. When we have strong coupling, then there are two eigenmodes. And then when we go to weak coupling, we have just single mode, but whose emissivity is nearly unity. Look at this, the peak of this emissivity is nearly 10, or actually here it's the exit ends, the energy, it's the highest, while the Q factor continuously, or this spectrum of emission, bandwidth of emission continuously narrows as we reduce the coupling between them. Okay, so we break the trade-off between peak emissivity and spectral selectivity. Okay, so we did full wave simulations of our system and saw very similar behavior, peak emissivity 1, and then continuously increasing Q factor. And then we saw that in the strong coupling regime, we have Rabi oscillations, but not in the weak couple or PT broken regime, in which we have different dynamics. And we did build this device just using standard nanofabrication, and then measured thermal emission while heating the sample at 700 degrees centigrade using an FTIR. Okay, so we first, in fact, this is an array. So I skipped a few details of how we designed this. We actually want very local modes in the system, for which we actually use the concept of bound state in continuum. So we designed this hexagonal lattice in which we localize the electric dipolar modes in individual silicon resonators. And we have a flat band here, which is that localized mode in the system. So if we look at the thermal emission from the system, we actually see it has no dependence on angle, which is the indication of this flat band in our system. Okay, so we saw that in experiments. And after that, in experiments, we just made samples with different magnesium fluoride spacer thickness. So when we had 0 magnesium fluoride spacer thickness, that was the strongest coupling. And as we increased the spacer, the coupling reduced. And in experiments, we saw that these two modes will merge into one and eventually just give out a single mode with Q factor of about 40. And at this temperature, 700 degrees centigrade, 40 Q factor 40 is so far the highest, and it's limited only by the losses in materials at high temperatures, especially silicon at this temperature. Okay, so in fact, that way we are hopeful by changing the material to instead of silicon to something like, for example, iron sulfide or other materials, we could get the Q factor even higher, close to in fact 1000. So that's what we are currently working on. And more importantly, we said this system would actually break the trade-off between emissivity and say spectral selectivity, and that happens exactly because of what we see here. So in the weak coupling regime, here is the gradient of Poynting vector, which shows that all the thermal photons originate from tungsten. But these photons are effectively stored in silicon. Okay, it's the photonic mode of silicon which stores all these photons and then gives very high Q factors. But in the PT symmetric regime, that is a strong coupling regime, both photonic and plasmonic modes share the energy storage, and hence we don't get a great benefit in terms of Q factor. Okay. So what we are currently doing, in fact, further is if we change the angle of collection from zero normal incidence to oblique incidence, our system has even other modes. So which is, for example, the vertical mode here, and they all couple, which make this a 4x4 system, no longer just a simple 2x2 system. Actually, a 4x4 system, which has very interesting angular properties which come from topology. Okay, so if we look at the topological property, that is, do the K-sweep, K-space exploration of the property thermal emission of the system, we see that the eigenvalues split on two ends, but on certain or in specific range of K-space, we see that the eigenvalues coalesce into just one sheet, and the sheet is no longer just an exceptional point, but actually an exceptional surface. Okay, so we call this exceptional concentric ring, where we see that the topology is actually known as Z3 topology. So have plus half topological charge on one side, minus half on the other, and they both are connected through this exceptional surface, which is Z3 topology. So which means we'll preserve the directionality, the contrast in thermal emission, the spectral selectivity, all of them on this exceptional concentric ring, and which is extremely important in making directional thermal emitters. And that's what we are currently doing, especially for applications in espionage, security, etc. Okay, if there are questions, please let me know. I'll be happy. I think I have one here. Okay. Oh, okay. Excuse me, sorry, there was a chat and I just thought it was a question. Okay, please feel free if you have a question to ask me. So with that, what I would like to conclude my first part of the talk is non-Hermitian physics is really interesting in getting a different perspective on how to design thermal emitters, because it gives us very powerful parameters of design, that is symmetry, phase, and topology. And with that, we could design thermal emitters that are directional, that have good suppression, and at the same time can achieve very high efficiencies in terms of thermophotovoltaics, where even 50% should be possible with the system. We are currently, in fact, building one such TPV system to measure the efficiency of a non-Hermitian thermal emitter. So in conclusion, what I think non-Hermitian physics gives us is it brings an imaginary access to nanophotonics. So that's what I think of non-Hermitian physics for nanophotonics. Okay, so this is just an application for energy that I have mentioned. Of course, there are many other applications as well, which my group is working on. And in the interest of time, I just focused on only the energy aspect of it. In the next part of the talk, I'll move to a different material system where the phase transition is not optical, but actually electronic. So have a strongly correlated material where the phase transition is because of strong correlation in the material, that is electrons talking to each other like as if a jelly. And then now when I shine light on the system, the whole jellium or this connected electrons, they all interact with light together to give much a bigger response than what we would see before or without that. And this is really useful for making tunable nanophotonic devices, and that's what I'll be talking. Okay, so for tunable nanophotonic devices are needed for many emerging applications, which include lidars for self-driving cars or even optical computing, 3D displays, virtual reality, many things. In fact, recently, I think Gates Foundation announced that they would be funding VC on metasurfaces for imaging, so tunable metasurfaces for imaging. So clearly, that has a huge potential for revolutionizing how we image or display. Okay, so but the key component for that is tunable materials, tunable optical materials. Without that, we have no tunable functionality. And if you look at the past and then see how tunability is achieved, there are many different ways. So field effect modulation, apply an electric field that attracts charge carriers and changes the optical constant ever so slightly that you can tune the optical functionality. So that's one of them. Mechanical tunability, so where you stretch or deform your material, that changes the optical constants. MEMS also does the same thing. Elastomers, in fact, they're triggered by electrical stimulus, but they also deform and then change the optical constants. So those are a few demonstrations. And then just from chemical effects, you have photochromic effect, like changing the chemical composition of the material, or electrochemical effect, Applying an electric field changes the chemical composition, or you can also have chemical reaction, which totally changes the material and changes the optical constants. So if you look at all these applications, just generally from a bigger picture of it, the applications are either very slow. For example, MEMS, you cannot get a free or a speed like megahertz. Currently, if you buy, for example, DMDs, the state-of-the-art MEMS devices, you have speeds less than a kilohertz. They're just about 100 hertz or so. So it's really slow in tuning, but you can have larger tunability there. Or you have things like field effect, where you can have megahertz or even gigahertz tuning, very fast tuning. In the extreme case, ultra fast nonlinear stuff, where you can have even terahertz of tuning speeds. But the problem is they're extremely tiny. The index change that you get is not in the first decimal place, but actually in third or fourth decimal place. Okay, so you have either slow or very small. So can you have something in between? Can you do something better than either of the ends? Okay, so we thought, okay, that comes, this limitation comes only because light is interacting with single particles in all of these materials. And that's a mechanism for tunability. So what if we pick quantum materials where we have collective response? So electrons talk to each other and they all respond together. So then we can have much larger tunability and then also perhaps even megahertz response. So how to do that? So for that, we in fact started looking at a material which is 1T tantalum disulfide. So tantalum disulfide is a charge density wave material. It has charge ordering. So what I mean is 13 tantalum atoms slightly displace, okay, they come move inwards very slightly and in such a way that they support a single charge in this domain. Okay, and the single charge, in fact, there are many such domains in the sheet. So this is a 2D material. So in each sheet, there are so many such charges, and they all are interacting with each other via Coulomb interaction. Okay, so this is the concept of charge density waves. And this material, in fact, at very low temperatures, exhibits this fully condensed charge density wave system. We call it CCCW or commensurate CDW state. And at room temperature, it exhibits this nearly commensurate CDW state. So where you have domains of this condensed domains or charge ordering and surrounded by a few domains which are not condensed anymore. They are just free. So it's like it's a case of polycrystalline versus crystalline material. So this is an equivalent of polycrystalline. You have grains of different domains, but in between them at the boundaries, you don't have the perfect crystallinity or charge ordering. Okay. So because of this different phases in this material or electronic phase transitions, this material has been extremely studied because of, in fact, electronic phase transition at room temperature or above room temperature. And it has been shown that the electrical properties tune significantly with any stimulus, pressure, temperature, doping, and then field effect, both vertical field, in-plane field, so many different stimuli. Okay, so we were really curious to find out if this is also true with optical properties. And there was nobody who had any optical properties measured. So what we took was we peeled off, we exfoliated mechanically a 80 nanometer thick crystalline film and then created contacts and then applied a DC bias on this. And we measured the optical constants as we applied bias. What we saw was the refractive index changed, and it changed nearly up to first decimal place, which is huge. And we were extremely surprised. Why do we see so huge change in visible frequencies? Okay, that's quite a high photon energy when compared to, for example, the CDW band gap. Okay, charge ordering gives rise to a band gap which is about 200 millielectron volt in this material. So why do we see such a big change in visible frequencies? Okay, and with AC bias, we again saw something similar, change on the order of 0.1 index change, and for even just a bias of 0.5 volt, this is amplitude of 0.5 volt AC in this. So why do we see this? This was very surprising to us. We thought maybe light is doing something. Let's actually study carefully what light does. So we first started with very low intensity white light. So when I say very low intensity, we actually picked 10 milliwatt per centimeter squared, which is roughly 0.1 sun. Okay, so with 0.1 sun intensity, we characterize the optical constants. So this is a uniaxial material. So in the plane of the layers, we have this blue optical constants. And in the direction perpendicular to the layers, which is C-axis, we see this extraordinary or this red optical constants. So in visible, it's basically just a lossy dielectric, nothing special. Okay, but what happens is as we increase the intensity of illumination, we see that normal incidence will not change anything, but oblique incidence will change reflectance. So what does that mean? It means the extraordinary epsilon, that is permittivity in the c-axis direction, must be intensity dependent, not the in-plane permittivity, not the in-plane optical constants. Okay, so that's what we realized and then extracted this out-of-plane permittivity as a function of this white light intensity. Again, I'm stressing this is white light. I don't have any lasers. And then to give you a perspective, 100 milliwatt per centimeter squared is just one sun intensity. That's like holding tantalum disulfide in sunlight. Then I have so much change in index. Okay, we were really curious why this is happening. It's a huge change, and we wanted to see how fast it is. Maybe we thought there is something to do with okay, the stability of the material. Maybe it's reacting or something is happening. So we did even stability studies, etc. It was really stable. We could do all these measurements in just air, ambient air, and even 3-4 days, this material was totally fine. We didn't see any degradation. What we saw in terms of speed was this actually has a submicron speed, about 300 nanoseconds of speed. Okay, so we fit this transient, so we did pump probe measurements with the two exponentials. Again, just to remind you here, we are using laser with intensities much higher than white light. So we also had a little bit of photothermal effect in this. So we separated both the photothermal effects and something else separated from this, and then made sure which one is photothermal, which one is not, by doing additional experiments that I didn't show here. For example, changing the substrate or including substrate with different thermal conductivity. Okay, so what we figured out was in this process, we found out that it's actually the mechanism of optical tunability cannot be free electron generation. We just have too low intensity with white light to cause so much change in index. And it cannot be nonlinear optics. We didn't see any higher harmonic generation, no Kerr effect or Pockels effect, nothing like that. It was not anything that was related to photothermal and hence thermo-optic effect, that is light causing heating in the sample and heating changing the optical constants. So with white light, we saw that we cannot have a temperature change beyond 0.5 degrees centigrade, even with the most lenient calculations or parameters in this model. So that cannot be the reason. So it should be something related to the strong correlations then. So what could that be? So that's what we were really interested in or curious about. And it also happens only in the c-axis. So why is that the case? So for that, in fact, what we thought was just then there were a few papers in which were doing band structure calculations on tantalum disulfide. And what they said was this CDW domains or charge density wave stars, this David stars, so they can actually stack on top of each other across layers in many different ways. And that can change their c-axis properties, electronic properties dramatically. Okay, so for example, in one case, you have this kind of stacking. So the stars stack on top of each other and then stagger, top of each other, stagger, etc. This is called AL stacking. So if you have this kind of stacking, then this material has a clear band gap here. So which means in the c-axis direction, this behaves like a semiconductor. Okay. On the other hand, if the stacking were all on top of each other, which is A stacking, then we would see that this material is a metal. So the density of states at Fermi level is no longer zero. Okay, so this can actually be show metal to insulated transition just by changing how we stack. Maybe that's what is causing the optical constants to change. That's what we hypothesized. So we said here is what happens. So at room temperature, probably both these kind of stackings happen. So here the gray stars are the bottom layer stars, and the hollow stars are the top layer stars. So the blue domains have staggered stacking, while the red domains, red structures, they have center to center or stacking on top of each other. Okay, so you can have both of them, but energetically blue stacking is favored. Okay, so they're probably more in number. So when I shine visible photon, then it can happen that all of this domain will absorb this photon energy and then quickly share this in such a way that this domain either melts or dissolves or only changes at the edges. We still don't know exactly how things happen. We are yet to figure out. But at least this domain changes its stacking order and then emerges in the other form of stacking, so which is center to center stacking. And this is the reason why we seek optical tunability. So this is what we made as hypothesis, okay? Then we built a simple phenomenological three-level model. We extracted the key time constants from our pump probe measurements, and then we could predict what is the fraction of CDW domains that will be in this red stacking, so that is center to center stacking, and what is the fraction in the staggered stacking. So here is the calculations. Okay, we saw that the intensity dependent fraction of stacking of fraction of domains in the center to center stacking to be like this. Okay, so here is the intensities that we considered in experiments. Then using those numbers, we could use Maxwell-Garnett's effective medium theory to predict how the optical constants change. And we predicted the optical constants change, and they matched surprisingly well with experiments. And we were really pleasantly surprised and happy to see that this could actually vindicate our hypothesis, which is it's actually the stacking which changes the optical constants. So stacking of CDW domains is a new degree of freedom that this material exhibits, which we can change just with light. Okay, so this gives us tunability. So this has many different physics implications in terms of even superconductivity. Okay, this material, if we suppress charge ordering, it will actually show superconductivity. So maybe we could actually shine light and then cause the charge ordering to weaken, and then eventually let superconductivity emerge. So we might be able to see light-induced superconductivity in this material, right? So we are really excited to see if that is possible. So that's one of the directions in which my group is currently looking at on the fundamental physics side. But there are a lot of applications, of course, that are waiting for a tunable material like this. So we just wanted to make a simple grating, a meta grating. So we've made a simple device here, a grating device, and then measured the diffraction strength at two different wavelengths. This is not even an optimized device, and already we saw about 10% modulation depth at 512, 514 nanometer wavelength, and this is a millimeter scale device, okay? And this is optically tunable and very low power of operation. And 100 milliwatt per centimeter squared is just one sun intensity, okay? And then we further optimize this device to make it blaze grating. So in the blaze grating device, we could see even larger modulation. We could get 100% modulation depth. We have megahertz bandwidth. So this is 10 per 3 kilohertz. So this is megahertz. So we have about 3 megahertz or so as a bandwidth, no moving parts, and at the same time, extremely low power operation, less than 1 sun for tunability. So that can be a huge game changer in the upcoming tunable optical devices or tunable nanophotonic devices. And that's where we are currently working on in showing, in fact, a hologram that can show differently with different intensities. Okay, so that's a work in progress. And with that, I would like to sum up this part of my talk, where at least hopefully I have convinced you that tantalum disulfide and many such, in fact, quantum materials are extremely promising for tunable optical devices or even optical sensors, only because we now have response from this material not coming from single particles, but actually a phase transition that happens because of collective response. Okay, so all the electrons participating together in interacting with light. So we showed that the charge domain stacking is an important parameter in the energy landscape of the system, and light is a powerful knob to tune this energy landscape, to sculpt this energy landscape in this material. Okay, so with that, I would like to thank my group, especially Weiji and Lee, who did all the work on tantalum disulfide, and Chloe and Sakit, who did the work on thermophotovoltaics. So with that, I would like to thank you and also the funding agencies who supported this work, and I'm open for questions.
Thanks a lot, Guru, for an excellent talk and for sharing your most recent results. We can have a few questions. So Manu has a question. Manu, please go ahead.
Yeah, thank you, Prof. And yeah, thanks. It's really a very interesting talk. I have basically two questions. The first question is on the first part of your talk, where you showed about the filter that you designed for the emission and also to observe the light, which is not in the filter regime, right? So I was wondering what actually decides the wavelength range of your filter, because I noticed that you choose the emission wavelength range to be at the maximum of the black body radiation. So basically, what I think is that if you, because there you have large number of photons particularly, right? And if you can actually kind of observe that, not emit it, but it can actually enhance the emission, right? I mean, what exactly is the one that decides that wavelength? I mean, can it be changed, and I mean, how it affects the efficiency of it? This is the first part of my question. And maybe, I mean, second part is on the second part of your talk, where when you're talking about the stacking of the charge density waves, right? And it basically is that it's coupling to the z-axis of, I mean, the light coupling to the z-axis. So I was wondering whether did you, I mean, like, was there any kind of measurements done to check the efficiency, like the stacking efficiency, like with respect to the incident angle? Because if you couple, if you go more oblique to the incidence, so then you can actually efficiently couple to the z-axis. So was there kind of study done or something like
Yes, yeah, good questions. So let me go to the first part. So where you talked about the center wavelength of emission, and you, as you rightly pointed, we picked the temperature and the wavelength in such a way that Wien's law just tells us that's where maximum power comes out. It just is easy. But what about efficiency? Okay, so for the overall TPV efficiency, in fact, you want to be slightly at a bluer wavelength than the peak of emission. Why? Because bluer wavelength means you can actually pick a higher band gap material. Okay, for PV cell, a higher band gap would actually means even a slightly a small change in the increase in the band gap would means that your dark current from your PV cell would be exponentially smaller, right? So if your dark current is exponentially smaller, then you're going to have much larger open voltage circuit, open circuit voltage in your PV cell. So efficiency just goes up. So in fact, the optimum that we had in our studies, etc., would actually tell us that if you choose the center wavelength of emission to be, let's say, 3 micron, then your operating temperature should not be 900 Kelvin, but actually slightly less than that. In fact, it's best if you use like 700 Kelvin, then use a 3 micron wavelength. Or if you want to use 900 Kelvin, then maybe move to 2 micron wavelength.
Okay.
So of
Thank you.
course, this depends on the whole system optimization, which we anyway have to do. There is no way.
Always a trade-off.
Exactly.
Okay. Thanks.
So that's about the first part, and for the second part, it's very interesting. So some of the things that I skipped, I thought maybe they're boring. Was in fact we have flakes, like our samples are just a very thin, small area samples. We don't have really big area samples, at least in the beginning. Then we had just 80 nanometer thin flake. It was also a very thin, very small area flake. So now how to do reflection and transmission of this material or ellipsometry? It's almost impossible, right? Otherwise, you cannot measure angle result, reflectance, transmittance, that you cannot extract optical constants. So what we did was we actually put this in a microscope and then did, instead of doing the regular spectroscopic imaging, we had a spectroscopic imaging microscope. We just turned into Fourier imaging spectroscopic microscope. So we had to do Fourier filtering as well to choose particular angles and thereby actually get angle resolved emission or angle resolved spectrum from my sample, both reflectance and transmittance. And from that, we were able to extract epsilon in plane and epsilon out of plane. Okay, C-axis and the in-plane axis. So that was the characterization. But how do you couple light more into this vertical axis? And exactly for that reason is why we use the plasmonic gratings. We could have used even dielectric gratings, but you know, when you have plasmon resonances like metal, you always have very strong vertical fields, right? Your polarization is in plane, you have strong out of plane fields, and that's why we actually see this tunability enhanced. So there are two component devices. So one is choosing a material that has huge tunable response, so which is the first part. And the second is build a great antennas that can couple this with the material or the tunability of this material into a far field functionality. And plasmonics in this case helps us do that. course, dielectrics also, I think vertical resonances in dielectric resonators, which of course Ranjan's group has demonstrated before. Igal Brenner's group has demonstrated similarly very high Q vertical resonances, etc. I think those designs also should work in our case. Yeah.
Okay, thank you very much. Yeah, great. Thank
Alexander, please go ahead with your question.
I really enjoyed listening to your talk. I actually read a few of your papers a few years ago, and they did some proposals and actually even measurements here on it. But anyway, my question is of the light intensity levels and the physics related to the effects which you're describing, because the maximum intensity which you presented is 1 watt per centimeter square. So if you go from this point to the extreme values where the material starts melting, are there is any interesting effects or any interesting physics, or it's become saturated and boring?
Yes, yeah, that's again a very good question. We still don't know the answer. So what we did was we did 1 watt per centimeter square, and then after that, so we did actually laser characterization where we had from 32, I think 32 watt per centimeter square to about 120 watt per centimeter square. So in all of this range, we did see tuning, but we also had very strong photothermal effects. So this material is also sensitive to temperature. So if I change temperature, from a three-level model, you can assume that the relative population of different phases or different stacking will change, right? So temperature can also bring in tunability. So we were seeing only that part, then not actually just to find out the stacking change that light is causing to change. So we just wanted to isolate and hence stuck with only the low intensity range, but high intensities, I think clearly there will be a phase change that comes from just heating. And recently, I think there's also been a science paper where they did ultra-fast TM studies on this material, and then showed that if you just hit with a pulse of laser, ultra-fast pulse of laser, intense pulse, then at the moment the temperature increases so much that you have heating, and the material goes from phase transition, actually goes from nearly commensurate to incommensurate phase, and then eventually as it cools, it nucleates new domains and then goes back to nearly commensurate phase. So that will also bring in tunability. But it's a very different kind, and also the temperature ones are very sensitive. I mean, in my experience, it changes quite a bit from sample to sample, and even how you make the thermal contacts with the substrate, etc. So that's what we found out. Yeah.
Thank you. Maybe I can contact you in future if I have some more detailed questions.
Sure. Yeah, I'll be happy to discuss more. Yes.
Harish, please go ahead with your question.
Hi, Guru. Thanks a lot for your wonderful talk. Truly inspiring. So I have a quick question on the second part. So you have this Maxwell-Garnett-based model for your optical response as a function of the fluence, right? So what is the inclusion in this model? What is the inclusion and what is the matrix medium? I'm just curious to understand.
Oh, yeah, cool. Yeah, that's a great question. So we just had two stacking here, right? So we assume that in nearly commensurate state, I think literature shows that about 90% at room temperature, about 90% of the tantalum disulfide is all condensed. Okay, so if we assume that 90% has two kinds of either one versus the other kind of response. Okay, we don't know what it is. Let's say the blue has epsilon blue, and then the red has epsilon red, two kinds of epsilons. Then if we know the relative fractions, we can find what is the epsilon for any different mixing of these two, right? So that was actually what we did. So in fitting this, in fact, you can see the lowest intensity, you don't have any fit curve here. There's only measured. That's only because you have to find out what these epsilons are with at least just one value, right? So that was a fit. But what we did is we didn't have any free parameter and then just fit for one curve, and this was good for every other intensity. So that was the surprising part in our case.
I see. Very interesting. Works well, actually, the model. Thank you.
Guys, it's a strange coincidence. 9 years back, it was Harish who introduced me to Guru at the Clio conference. Excellent talk, Guru. I think there are no more questions, so I will ask you a question. So has anybody measured superconductivity in tantalum disulfide?
Yes, yes, good question. Yeah, pressure-induced superconductivity and strain-induced superconductivity and doping-induced superconductivity. What else have I seen? Papers on even bias-induced superconductivity, and even some of them actually thickness-dependent emergence of superconductivity. When you make the tantalum disulfide extremely thin or sandwich with different materials, you can change this charge density wave stacking. Actually, at many of these papers, they actually don't consider stacking as an important dimension in the energetics, just because it was not known before. But they all, like some of them show that, for example, superconductivity emerges if you had this material, a single layer that is sandwiched between HBN, two HBN layers. And somebody says, okay, if you had instead of HBN, maybe some other like aluminum oxide on both the sides, you won't see superconductivity. And there are such kind of discrepancies in many reports. But now we know that actually those happen only because depending on what you cover this or encapsulate this material, your Coulomb interaction between all these different domains can be very different. Their energy changes. And because of that, the stacking, the energy difference between different stacking completely changes. And that's why your tunability or even suppression of charge order or emergence of superconductivity, they all must be now varying in the samples. And that's actually what motivated us to look at possibility of light-induced superconductivity.
Yeah, very nice. Guru, do you know at what temperature it superconducts?
Yes, this is about 7 Kelvin. I think that's the highest that I've seen with pressure-induced tunability,
Okay.
superconductivity.
Okay. Thank you.
Yeah.
I think there's a question from Yogesh. Yogesh, go ahead.
Hi, Guru. It's a nice talk. So, what kind of fluence level you are expecting that it will generate the light-induced superconductivity?
Yeah, so that's again a good question because we don't know. There is in fact one paper which already shows one such light-induced superconductivity, but actually there they're using ultra-fast light, and the light-induced superconductivity is actually heating. So by heating the sample, the charge density waves are just they melt away. You move away from commensurate phase to all the way to incommensurate phase where the charge density waves are completely gone, and hence superconductivity comes up. So that was not surprising. People knew that, but at least there is a report which showed that you can do this with ultra fast laser. I don't remember exactly the numbers, like fluence number, but I think the numbers were quite high with that because it was actually photothermal effect. But what we think we can do is you don't need photothermal effect to do this. You can do that completely by a different mechanism, which is stacking. Just change the stacking. I just mentioned a few of them. One of them is actually encapsulating to control stacking. And the other one is, of course, light itself. But you can also control it by even things like, just think about if you were to take single layers of tantalum disulfide, twist, stack, you would completely change the energy dynamics of this material, right? So the stacking order comes only because of particular crystal structure. Now, if you twist, that is completely different, and the Coulomb interaction is now all different, then you have new energy landscape of the material. So you can, in fact, there's so much unknown and then free parameters in the system. I feel that this is a great opportunity to explore more of this light matter interaction.
Definitely, manipulating stacking is more interesting than photothermal effect.
Yes, exactly. Yes.
So if there are no more questions, guys, we must thank Guru for such an enlightening talk. Guru, we enjoyed your talk so much, and congratulations for such wonderful results. And we'll keep the discussion going. Yogesh, my postdoc, he has some interesting results also on light-induced superconductivity, but mainly in IBCO
Okay.
type of materials where we are looking at the balance between the superconducting and the charge density wave phases.
Really cool.
And
I was about to talk about the stripe phases of IPCO, relate the CDW to this. I think we should surely talk. Yes.
yes, yes, yes. So have a very good night, Guru. Thanks a lot for devoting so much time and sharing your most recent results with us. Thanks a
Thank
lot.
you. Yeah, it was really nice to see you all, and thank you for your time. And hopefully we can meet in person and have more science talks. Thank you.
Sure. Thanks a lot, Guru. Bye bye. Take
Bye.
care. Yeah, take care.